One of the most useful skills, and actually like easiest with vectors, is converting polar vectors, which are the kinds that we see in real life, to rectangular vectors, which are the kinds that are much more easy to manipulate mathematically. So the difference between polar and rectangular: rectangular is your classic x and y grid. It tells you how much horizontal and how much vertical is at play. Polar is a lot more like real life. Like if I said, hey, take this thing and drag it over there, I'm not going to say like walk 10 steps that way and then turn 90 degrees and walk 5 steps that way. I'm just going to like point to where I want you to go. In real life, we just point in the direction of things that we want to go. We don't give precise x and y components. And even the way that like planes work and radar work, we've already gone over this. Like they look at which direction something is and how far away it is. So polar does the same thing. It says 450 units out, 75 degrees. The vector is the same thing. This represents the magnitude, so like how powerful a force is. And then the direction just tells you which direction it's pointing. These directions are the exact same as they would be on the unit circle. So 75 degrees, you know, is in quadrant 1, which you can see I've kind of represented here. But polar are really, really difficult to do math with. So even though they make a lot more sense to us in terms of how much something is going and in what direction, they are a little bit trickier to operate with. So converting to rectangular is super useful. Now, the way that we do this is quite simple. You just take this vector, and since we know that every vector is made up of a vertical and a horizontal component, then all we've got to do is use our trig to go backwards from here. So we'll label this side V for vertical, and we'll label this side H for horizontal. But it's also really useful to remember that this vertical side is opposite the central angle, and that this horizontal component is adjacent to the central angle, and then the magnitude is the hypotenuse. That's actually like, we used Pythagorean theorem to find the hypotenuse, a squared plus b squared equals c squared, when we went from rectangular to polar. So now that we're going backwards, it makes sense that we would still think in terms of hypotenuse, opposite, and adjacent. Now, the ratios that we'll use, you're super familiar with. The sine of that 75-degree angle would be equal to opposite over hypotenuse, or in this case, the vertical component over the hypotenuse, which is 450. Think briefly about how you would solve this for v. You'd multiply both sides by 450, so 450 times the sine of 75 degrees, I should stop capitalizing that, don't be dumb, is equal to v. And then from here, you're going to want a calculator, because most of the time they give you stuff that you haven't necessarily had a lot of unit circle practice on. So 450 times the sine of 75 degrees is 434.6. So the vertical component is 434.6. And then that's makes sense, because like if you look at the way 75 degrees is pointed, this vertical component looks really long, almost as long as the hypotenuse itself. So if the hypotenuse or the magnitude is 450, it makes sense that this would be about 434. The horizontal component is going to be a lot less. If I were estimating, like if that's 450 and this is a chunk of it, I would say somewhere closer to like the 100 range, maybe even less than that. We're going to do the same thing using a different ratio, adjacent and hypotenuse. So we could do the cosine of 75 degrees will equal the horizontal component over 450. So again, how you would solve this, same as before, take 450 times both sides, and I'll get the horizontal component alone. Use the calculator, and I got 116.5. Cool. So now, instead of having to express this as a magnitude and a direction, I can express this exact same vector in terms of its horizontal and vertical components, and that'll be a lot easier to do math with later on. One thing that you may have noticed is that I used sine to calculate the vertical, the y component, if you will, and I used cosine to calculate the x component. If you think back to your unit circle, you might remember that sine was always the y coordinate of the unit circle, because that was always the opposite side, and cosine was always the x, the adjacent side. So the same like axiom that you learned about sine always being vertical and cosine always being horizontal hold true here, and you can use that to your advantage to help save you the trouble of trying to like draw it out and figure out what everything is. If you are confident and comfortable remembering that sine is the vertical and cosine is the horizontal, then you're in a really good place. So my final finished answer, I just got to put these in order. Horizontal, or the x component, comes first, so 116.5, and vertical comes second, so 434.6. Very cool.